that you shall stretch your hand of blessing upon him, that whatever he's coming to present, he shall present it with confidence, with dexterity and succinctness, and that the participant will as well absorb and understand whatever he's here to present. And that at the end of the day, glory and honor shall be given unto your name. With this and many others, we ask you, Christ, our Lord Jesus Christ, your Son, who lives and reigns with you and the Holy Spirit, one God, forever and ever. In the name of the Father, and of the Son, and of the Holy Spirit. Amen.
Amen.
Amen. Thank you so much, Mr. Godwin. Okay, so we move to the next item on the agenda, introduction of resource person, and that will be done by Mr. Gilbert Owusu-Efriye. Mr. Gilbert, Honorable. Hello, Mr. Gilbert, are you here? Please, can anyone hear me?
Yes, please, we can hear you.
Oh, okay, so Mr. Gilbert, I think he's offline. Okay, then I'll just do the introduction of the resource person. Okay, so Mr. Clement Chumesi is a PhD candidate at the Cardiff University. Mr. Clement is currently a final year PhD mathematics student and the Vice Chancellor Scholar of Cardiff University, United Kingdom, with specialties in mathematical modeling of infectious diseases and biological systems. Mr. Clement has expertise in statistical and mathematical modeling, which includes but not limited to stochastic modeling, regression modeling, disease modeling, functional data analysis, machine learning, Markov models, Bayesian networks, approximate Bayesian computation, and time series models. So Mr. Clement Chumesi is our resource person for today. All right, so we move on to, we'll now invite Mr. Clement Chumesi to take over now and give us a presentation of what we are about to do today. Thank you so much, everyone, and I hope you enjoyed this program.
Okay. All right. Thank you very much for the opportunity. Unfortunately, Gilbert, I don't know whether he's still sleeping. All right, so I'll just share my screen and then start with a brief introduction. Okay, as the host rightly said, my name is Clement. I'm a final year PhD student at Cardiff University, and I do mathematics. So today I'm very happy, and also I'm also the president for Ghanaian students in Wales. So I'm also happy to also impart knowledge as well and learn from each other. All right, so today's topic is actually going to be dubbed general knowledge on statistics and then data analysis. So basically, statistics is very broad. So I'll try as much as possible to condense it. So this is just going to be like an introduction where you can build upon. I didn't originally plan to use slides, but later I realized that making the slides will help the presentation to be more organized and then help me with planning of my time as well. Okay, so we are not going to spend much time, but I'm sure we'll spend at least an hour or more maybe not more than 1 hour 30 minutes, but I'm sure it's between 1 hour to 1 hour 30 minutes. Okay, so or we could even finish earlier. All right, so okay, so this will basically be the outline of my presentation. Let me maximize this one first of all. Okay. All right. So this is going to be the outline of my presentation. So basically, I'm going to first of all give a brief introduction to statistics and some related fields, and I'll give a useful information about data analysis, and then I'll talk about regression analysis and variable selection techniques. Technically, there are a lot of models we could have looked at, but I wanted to condense and restrict myself because it's a very broad field. So the only thing we can do is to kind of restrict ourselves to certain, let's say, analysis or models, and then we can build up from there. And then next one is we are going to, that's the last but not the least, we are going to talk about some statistical softwares available and the advantages over the other. Okay, so first of all, what is statistics as a field of mathematics? So keep in mind, mathematics as a field has so many branches. So basically, we have pure math, we have statistics itself, we have operational research, we have data science and analytics, so many fields. Even biostatistics, they are all branch of mathematics. Indirectly, they are also branches of statistics. So when you talk about statistics, what do we do, or what is statistics all about? So statistics is basically about collection of data, analyzing your data, and after analyzing, your interpretation is very key. And then after the interpretation, definitely it will be used for policy making. It will be used for further explorations. So basically, statisticians help us to learn and understand better about any phenomenon based on the data. Okay, and the field of mathematics is in a little way very correlating and interdependent on each other, such that for some reason statistics cannot survive alone without an application of, let's say, pure mathematics. And then let's say operational research is also another field which is closely related to statistics. So technically they do everything statisticians do, but theirs is more related to the industry. So it's more like they try to make sure they make their statistics very practical and very useful to the industry. It doesn't mean that statisticians might not also or cannot also do that. But I just want you to keep in mind so that in some future time when you're applying for maybe a PhD, master's, or any course, you also bear in mind that there's a whole course, especially in the UK, there's a whole course called operational research, which is very related to statistics. They do everything statistics. However, they try to do things that are very, very practical. So can we please mute those in the background? Can we mute our videos? There's a little bit background feedback from the background. Okay, so like I was saying, so operational research is closely related. So, but what they do is that they do a lot of optimization. They do a lot of so with the optimization, they definitely would deal with transports. So there are a lot of transport problems, and they do anything statisticians actually would do. And when you talk about econometrics as also a relevant field of statistics, so econometrics basically, as you know, if you know those who do economics. So in econometrics, it's all about time series, regression models, and so on. So they are all kind of adopted principles in statistics. Biostatistics is a form of statistics, but with emphasis on health or health modeling. Okay, so we even have bioinformatics, which is also closely related to biostatistics. And we now have a very, it's not recent, but it's recently developing, that is data science. Okay, so data science and data analytics is also now taking over, and they are all closely related. So these are fields that are related to statistics that you can think of. All right, so now one thing I want you to keep in mind is that when you talk about data analysis, okay, every single data analysis can be categorized strictly into two. So we have the descriptive and then inferential statistics. So basically, if I talk about data analysis, in essence, I'm talking about statistical modeling, and in essence, I'm just briefly talking about statistics. So keep in mind that statistics, in terms of data analysis, can be categorized into two. So we have the descriptive and we have the inferential. So in every study, you should make sure you have these two versions represented in your study. Okay, so when you talk about the descriptive statistics, it's basically trying to talk about the fact that you have a data. Like we said, statistics is all about collection of data, analyzing your data. After the analysis, you have to interpret, okay, and then they for other users of, or let's say beneficiaries of your results to take it from there, isn't it? So, and keep in mind that we expect to see some form of descriptives where we are summarizing the data. So the descriptive is all about data visualization and also giving some summary measures, like let's say trying to tell us about the means, median, mode, maybe kurtosis, skewness, and other information, which proportions and those kind of things. So basically in every, and then when I talk about the visualization, we are talking about the pie chart, the bar plots, the histograms. I mean, there are a lot of descriptive visualizations, as in data visualization, you can actually do. So keep in mind that that's always the first thing you do in any statistical research or in any research. So keep in mind that in any field you find yourself, at a point in time, you need statistics. It doesn't matter the field. So basically, the statistics is more like the building blocks upon which research can actually be made possible. So without statistics, you cannot actually make inference and make conclusions with confidence. It's actually statistics that makes all these possible. And then with the inferential statistics, keep in mind that with the descriptive, you are basically summarizing the data, but you cannot make meaningful deductions from it. So keep in mind that you can only say it appears that maybe the proportion of females maybe is higher than that of males, but you cannot conclude that maybe females are more likely to maybe get COVID-19 than males, okay, until you do an inferential statistics. So the inferential statistics is actually where the hypothesis testing or the statistical test and then the statistical models actually come into play. Now, one thing I want you to keep in mind is that we shouldn't always confuse statistical tests with statistical models. Definition of model in different fields is very different from how statisticians or mathematicians define models. When you go to fields like maybe not necessarily psychology, but maybe sociology, maybe social work, how they would define a model, okay, even a conceptual framework that we would just define as conceptual framework, they can classify it as a model. But in the context of statistics, those are not like our definition of models, okay? So let me try and distinguish statistical tests from statistical models. Now when you talk about statistical tests, okay, statistical test basically deals with trying to test an hypothesis. And when you talk about hypothesis, it's just any statement which could be true or false, okay? And then always with hypothesis testing, there are two mutually exclusive statements that we are trying to test. But the null hypothesis is what we wish to test. But the null hypothesis always should contain the null statement. So always, like if you are comparing means, you should always say that maybe there's no significant mean difference maybe between groups. You don't say there's significant mean difference for the null. And keep in mind, it's always the null we test. But we do the hypothesis testing based on the alternative hypothesis, okay? I wouldn't go into much details, but I want you to have a fair idea that there is something we call statistics. So because I said inferential statistics encapsulate both hypothesis testing or statistical tests and statistical models. So basically with the statistical test, you are testing an hypothesis. And hypothesis could be any statement you are interested in, okay? And those statements, you cannot derive or drive in, conclusions based on the descriptive summaries or the descriptive statistics, because I said that descriptive statistics is just to give us a fair idea what is happening inside the data or what the data can tell us before we actually start actual inferential statistics. So as the name goes, inferential. So inferential means deduction. So it's after you've done inferential statistics, that's the only instant you can confidently make conclusions, okay? So keep that in mind. Now, so when you talk about the models in statistics, in the context of mathematics or statistics, it implies that there are some underlying parameters, okay, that we need to estimate, okay? So keep in mind that anytime you have an equation, any equation with unknown parameters, such that you can estimate those parameters, that equation can be termed as a model or a statistical model. So these are the things we have to keep in mind. So you realize that with statistical modeling, we are estimating parameters, but with hypothesis or statistical tests, we are not estimating parameters. We are rather testing hypotheses. But keep in mind that when you estimate the parameters, you would be interested in that is in the context of the statistical models, you'll be interested in identifying or concluding whether the parameters were significant or not. In that case, the statistical testing also comes in to complement it. So statistical tests and statistical models, in a way, they go together, okay? So keep in mind that there are two different things. One is testing hypothesis, but one is helping to estimate parameters of a model. And those parameters, we'll learn a little bit about what I meant by parameters. Okay, so there are some brief terminologies we need to familiarize ourselves with. And then, because since we are trying to study or get a good introduction of statistics. So when you talk about parameters in the context of statistics, okay, so like parameters is always any measure you compute from a population. So before then, when you talk about a population, okay, in context of statistics, it doesn't mean the whole of Ghana. It doesn't mean the whole of China. It doesn't mean the whole of like Shanghai. Okay, that is not the definition of population in the context of statistics. Basically, you are doing a study, okay? So when you are doing the study, you might be interested in a certain group. That group you are interested in is what we call the target population. Now, the total units or the total number of elements within that target population is just your population. Okay, so I could just be interested in studying, let's say the prevalence of, let's say, HIV, or let's say the prevalence of COVID-19, since it's actually the disease of the day. Maybe the prevalence of COVID-19 within, let's say, or among some private school in Shanghai. That particular private school, the total number of students within that school will be your population, okay? And then, so that will be your population. And any subset you take from that population is what you call your sample, okay? So I just want you to keep in mind that population does not mean the whole of a country, okay? So population is just, it's more like basically the group of interest, the total number or the total number of individuals within the group of interest. And then understand that the target population is always the group you're interested in. And then the total size is actually informing your population. And anytime you obtain a subset from it, or you select part of that population, that's when we call a sample. Now, when you talk about a parameter, okay, so keep in mind the definition of parameters is basically what was said already in the model part, because when I talked about the inferential statistics, I said we have the inferential statistics and we have the statistical tests and we have the statistical models. Now, when we talk about parameters, parameters are simply any unknown values, okay? Or so parameters are always unknown, but they are measures we compute from a population. Okay, so keep in mind that parameters are measures we compute from a population. And then statistic, don't confuse statistic with statistics. So the statistics is the subject, okay? Now the statistic is any measure you compute from a sample. So you can use this abbreviation PP, population parameter sample statistic, okay? So it implies that I can ask you this simple question. Maybe there was a class I wanted to look at, maybe the mean maybe GP of students in a certain class. And what I decided to do was that, first of all, I selected that class I'm interested in. So basically that class becomes my population. Now, if we ask this question, under what condition would the mean GPA of students in that class be considered as a parameter? And under what condition would it be considered as a statistic? What answer would it give me? If you're able to give me that answer, then that implies that you actually understand what a parameter, the difference between parameters and a statistic. So basically it implies that the average GPA of students in that class will be considered as a parameter if we consider the entire class in computing the average. But the very moment you consider a subset or part of the class in computing the average GPA, then that average GPA becomes a statistic. And keep in mind that hardly can we compute the parameters directly from the population, especially when your population size is very large. Okay, so keep in mind that the statistic or the sample statistic are always used as what? Estimate of the population parameters. So,
yeah, hello.
Hello, can you hear me?
Yeah, hello, I can hear you. Can you hear me?
Yeah, I can hear you.
Hello?
Yeah, I can hear you.
Hello. Ben Carson, Honorable Ben Carson.
Should I go ahead?
Yeah, please go ahead. Please go ahead.
Okay. So like I was saying that, so basically the parameters are any measures you compute from a population, but when we have large population size, hardly can you compute the parameters directly from the population. So we use the sample statistic as an estimate of the population. And in terms of estimate, it meant that the estimate should be good. So we have some characteristics of a good estimate. Any good estimate should have some peculiar characteristics. It shouldn't be biased. It should be unbiased. It should be consistent. It should be efficient. But you cannot get an estimate that satisfies all these conditions, the condition of unbiasedness, sufficiency, efficiency. But at least if it's unbiased, then it's good enough, because an unbiased estimator implies that its mean will be actually or will converge to that population parameter value. Okay, so just keep in mind that statistics are only used as what? Estimate of the population parameters. And don't confuse statistic with statistics. The statistics is the branch of mathematics. The statistic is any measure we compute from a sample. Okay, now what are the types of variables we have? And keep in mind, because we are going to deal with data analysis, we'll be hearing terms like variables. And when you talk about variables, what are they? So look at the name, variable. It implies we obtain it from the word vary. When we say something varies, we know that it's something that changes, isn't it? So it means that any characteristic, okay, that actually changes is a variable. Why is age a variable? Because if I talk about age, can't we get different values of age? Don't we have different ages? Meaning that as far as age changes, it makes it a variable. So anything that varies is a variable. Any characteristic that varies, height, we have different height, it makes height a variable. We have different GPAs, it makes GPA a variable. We have different colors, it makes color a variable. Okay, so keep in mind that is basically what variables are. We have something called random variables, which is a little bit in depth, which we wouldn't go into it because you don't really need it for your case. Okay, but for it's useful, but for your case, don't confuse variables with random variables. Okay, random variables basically assigns elements in something called a sample space, a real number. And I don't want to go into that information or that details because we don't really need it for this presentation. So how many types of variables do we have? Keep in mind that every variable or all variables can be categorized into two. So we have the qualitative variables and we have the quantitative variables. And it's technically out of that we had different types of research, where we had qualitative research and we had quantitative research. So as the name goes, quantitative means that it's something that deals numerically, right? So quantitative variables are variables that naturally take up numbers, whilst qualitative variables are variables that naturally do not take up numbers. Okay, I want to explain it in very basic terms so that anyone could appreciate, because technically people could have just Googled what the types of variables and you just be memorizing and pouring something. But I want to explain in layman's terms so that you can actually appreciate what we are doing. So keep in mind that we have all variables can be categorized into two, quantitative and qualitative. Qualitative variables are variables that do not naturally take up numbers. Okay, examples: sex, race, anything that do not take up naturally numbers. If I ask you what is your height, the first thing you mention is a number. If I ask you what is your age, the first thing you mention is a number. Okay, and that makes it a quantitative variable. But if I ask you what is your name, you give me a name. If I ask you what is your sex, whatever you say is just a name. Okay, if I say that what is your maybe your COVID-19 status, positive or negative, is just a name. So keep in mind that makes it qualitative. But one thing we have to be very careful is this: in research or in data analysis, these qualitative variables, we would assign some numbers to them. But assigning numbers to them doesn't make them a quantitative variable. This is something people should keep in mind. Assigning numbers to qualitative variables, and another name for qualitative variables are categorical variables. So when you hear the word categorical variable, it's the same thing as qualitative. Why? Because every single qualitative variable has categories. Every single qualitative variable has categories. So that's even one of the best ways to distinguish a qualitative variable from quantitative. So like I said, for every single qualitative variable, sex, if I say sex, don't we have the categories, males and females? If you give me, let's say, color, we have different colors. So you realize that for every qualitative variable, we have categories. So that's why we also call it categorical variable. So qualitative or categorical. And I said that for quantitative, they naturally take up numbers. So another name for quantitative variables are numerical variables. Okay. Now I was creating a disclaimer there. What I said was assigning numbers to qualitative variables do not make them quantitative. Okay. So in research, maybe let's say you had a variable called gender, sex, and it was males and females. Okay. But you realize that for the sake of maybe your statistical analysis, you needed to assign a dummy code to it. When I say dummy code, you are assigning maybe zeros and ones. So you gave maybe male 0 and female 1. With that, it doesn't mean that always that should be the order, isn't it? Because someone can even use 29 and 30 and just say that 29 means a male, 30 means a female, and it will still work in any software. It doesn't mean that I should always use 0 and 1. There's only one instance when you should strictly stick to 0 and 1. I'll talk about that when we get to the regression part. But apart from that, you can use, since it's a dummy variable, since it's a categorical variable, you can use any dummy variable. So, or dummy code. If I say dummy code, it implies I can use 0 for male, 1 for female. I can use 1 for male, 2 for females. I can even use 30 for males, 29 for females. And I just have to tell the software that 30 means males, 29 means females, and it will still work, right? So you realize that technically it doesn't take up numbers, but we can assign numbers. And the reason why we assign numbers is for us to easily be able to do further statistical analysis with them. But it doesn't make them what? It doesn't make them quantitative, okay? But there's one instance where there are certain variables that we cannot naturally measure. And we call them in statistics latent variables. So these latent variables, for instance, if I want to look at a company's satisfaction, I mean, let's say you are customers and we want to assess this, your level of satisfaction with some company, they would have something called a scale. Even your happiness, we have a scale for it. How sad you are, we have a scale to measure sadness. We have a scale to measure a lot of psychological variables. Now, those variables, you know that technically I couldn't have measured your happiness, isn't it? But we've been able to design a scale. When I say a scale, it's just a set of questionnaires. I mean, it's a questionnaire with a set of items, and those items together should quantify maybe your happiness or your love or whatever. But now keep in mind that after quantifying these ones, okay, in terms of the scale, in that case, you've in a way obtained something numerical. Okay, so keep in mind that if you have a latent variable, a variable you cannot actually measure in reality, but you only need to use some form of scales or use other information, which sometimes we term them as constructs to actually measure them. So what happens is that once you're able to get that scale and you actually quantify that scale, now whatever measure you have or the values you have, we can now tag them as something quantitative, okay? But once you assign dummy codes to, let's say, sex, or let's say, maybe, let's say, level of education, you assign dummy codes, it doesn't make them numerical. Okay, now we have something called scale of measurement. I wouldn't want to waste too much time there. Keep in mind that I said that we have two types of variables. We have the qualitative and quantitative. Now, if a variable is qualitative or categorical, it can either be a nominal variable, or it can either be a nominal variable or an ordinal variable. So when you talk about the scale of measurement, we have 4 scales of measurement, such that every single variable can fit into one of them. So the scale of measurement, we have 4. One is called the nominal, followed by the ordinal, followed by the interval, and the last one is the ratio scale. Okay, so basically, I'm just going to distinguish them shortly. I'm sure most of you, when you are doing any form of basic statistics in your course, your respective courses, you come to a point where they will ask you to be able to categorize some variables into these scales of measurement. I'm just going to give you a trick so that you don't have to memorize anything. You should be able to put any variable into one of these scales. Okay, so like I said earlier, So we have 4 scales. Now, and then we have the nominal, the ordinal. Okay. Now the nominal and the ordinal actually be qualitative variables would either be nominal or ordinal, and quantitative variables, okay, would either be interval or what, or ratio. Okay. So the very moment I ask you, let's say, what is the scale of measurement for, let's say, height, you don't have to think about nominal and you don't have to think about ordinal, because the height is numerical. Okay, so keep in mind that when a variable is categorical or qualitative, okay, there's a little bit of feedback. If the variable is numerical or qualitative, okay, one thing you have to keep in mind is that it will either fall within the nominal scale or the ordinal scale. Now, what is the nominal scale? So basically, I mean, at a point, just as humans, we learned how to do classification. You know, at a point, we could have called males, females, and we would have accepted it. I don't know whether you understand what I meant. We all grew up, or let's say we grew up, and one day we said, when you meet someone like me, call that person a male. You know, they could have said, when you meet someone like me, call that person a female, and we would have accepted it, because that's what we came to meet. So what I'm trying to imply there is that for nominal scale, they don't have any justification. They are just characteristics attributed by names, and there's no justification for that. And technically, every variable has a name, right? But so meaning that for something to be either in the ratio or interval scale is already nominal, okay? So the order that I gave you it's actually sequential. So the nominal is the weakest scale, okay, followed by the ordinal, but the two forms the scales for the qualitative variables. And then the interval scale, and then the ratio. So the ratio is the last one and is actually the most powerful. Now keep in mind that for something to be ratio, it is already interval, and it might not necessarily be interval, but it is already ordinal and it's already nominal. So keep in mind, all qualitative variables, all quantitative variables also have names, isn't it? So the mere fact that they have names, it implies that all quantitative variables would already have satisfied the condition for nominal and the ordinal scale. So I just wanted you to keep that in mind. Fine. Now for the nominal, what we said is that it's just by names, and there's no justification for the names. Now the ordinal is when now those names have some form of ordering in there. So the very moment I ask something like educational level, is it going to be a nominal scale or is it going to follow the ordinal scale? You ask yourself, educational level, do we have any form of ranking in there? And you can clearly see that educational level, we have some form of ranking. We have primary level, basic level, primary level, tertiary, and you could see some form of ranking in there. That makes it what? An ordinal scale. So always when you are asked to classify a qualitative variable into the two scales of measurement, specifically the nominal or ordinal, the first question, the easiest way is that ask yourself, is there some form of ordering? If there's ordering in there, then it's ordinal. If there's no ordering, then it's nominal. That is very simple way of classifying any qualitative variables into either nominal or ordinal. So if I ask you, let's say colors, yellow, green, blue, whatever, and I ask you what scale, you ask yourself, is there any form of ordering? Clearly, you cannot say yellow is bigger or better than blue or whatever. So in that case, it's nominal. Okay, so so for the qualitative, we are done with it. Now the quantitative, that's the part that I want us to really distinguish. And that's, so many people are always confusing themselves with the interval scale and the ratio. Now the interval scale and the ratio, they have peculiar things in common. I already told you that basically they are numerical, isn't it? So it means all numerical variables or any variable that takes up numbers would fall in one of them. But the main difference between the two is this. There's something called absolute zero. When you talk about absolute zero implies that it's like, when I say zero, it meant there's nothing. For instance, if I say I have 0 cedis, it means I don't have anything with me, okay? But if I say 0 degrees Celsius, it doesn't mean the temperature is 0. It doesn't mean the temperature is finished or is gone. 0 degrees Celsius has a meaning. It actually means that the temperature is cold. Okay, so it meant that 0 degrees is not an absolute zero. But if I say that there are 0 chairs in the room, it's absolute zero, meaning there are no chairs in the room technically. So the way you can distinguish between interval and then ratio scales is that use the absolute zero. That is the easiest way. What I mean by the absolute zero is that ask yourself, can that variable be zero? And if it's zero, does it have a meaning? And so if it is zero and it has a meaning different from the fact that it's empty, then it's interval. But if it can be zero and the meaning of that zero means emptiness, then it means it's ratio. So if I ask you, let's say number of chairs, which scale of measurement would you place it? Would you place it under quality, under interval, or let's say ratio? The first thing you ask yourself is that the number of chairs, if it is zero, what does it mean? If the number of chairs is zero, it meant there are no chairs, then it's ratio. But if I ask you something like, let's say height, okay, height of, let's say, humans, and I ask you, can the height of humans be zero? If it's not possible, okay, can height of a human be zero? Height of a human cannot be zero. So in that case, it meant that it can't be within the context of what? It can't be in the context of what? Ratio. So it can't be a ratio. But height at a point could be interval. So in this case, height is interval. But height at a point could be ratio, depending on the height of what subject are you talking about. So there are instances, maybe you are talking about height of something that is infinitesimally small, such that it could be zero. I mean, sometimes it could be thickness. I mean, we could have, thickness of something to be almost zero. So meaning that height as a variable, okay, could either be ratio or interval, depending on height of what are we talking about. So if I'm talking about height of humans, as far as we don't have any human being who has a zero height, it meant that there can be an absolute zero within the ratio scale. Another simplest explanation or way of distinguishing is that for the ratio scale, they can never be negative. The ratio scale, they can never be negative. So you realize that we can have a negative temperature, but you cannot have a negative height. We cannot have a negative age. We cannot have a negative, so it meant that once you cannot have a negative of some specific variables, they automatically also forms under the ratio. So with this trick, you should be able to classify every single variable into one of these categories. So I will just proceed. Okay, so the last item on this slide is about the types of statistical tests and models. I've already explained what statistical tests are and what models are. So for those who just joined, we said that for statistical tests, it's basically testing an hypothesis. But for models, we are estimating some unknown parameters. But after testing or estimating the unknown parameters, we need to test whether these parameters are significant, and then statistical tests also come in. So technically, models and statistical tests, they go hand in hand. Now, every statistical test or models, we have two versions of it. Statistically, we have three versions, but technically there are two. What I mean by there are two is that for every statistical test, we have a parametric and its non-parametric version. So we can have a parametric statistical test and its non-parametric test, which we'll learn very soon. And for the models too, we have parametric models and non-parametric models. But what I meant by, in some cases, there are three, is that we have semi-parametric models. Okay, so in the context of for statistical testing, we can have strictly parametric and non-parametric tests. But for models, we can actually have parametric, semi-parametric, and then non-parametric models. So I just want you to keep in mind, but broadly, in general view, we can classify any statistical test or model to either be parametric or non-parametric. Okay, so just keep that in mind. All right, so this is just to a graphical summary of what I described earlier. So I wouldn't go much into this. You would have these slides if you want. I technically initially I didn't want to use slides. I wanted to just talk, but I realized that it would be more interactive if I use some form of slides. Okay, fine. So basically this is all what I said earlier, that for the qualitative variables, they are either into nominal or ordinal scale. Once that qualitative variable has some form of ranking in there, then automatically it's ordinal. So if I ask you this question, that the brands of, let's say ranking of, let's say ranking of countries with respect to, let's say, GDP. So if I ask you something like ranking of countries with respect to GDP, you know, technically countries as a variable would have been nominal because there's no ordering. We cannot say Ghana is, you can only add ordering once you attach another characteristic to the countries. if you are talking about, let's say, the size of countries, then you can now have ordering. If you are talking about, let's say, the GDP of countries, then you can have ordering. In that case, it becomes ordinal. But when you're talking about countries without adding any form of additional characteristic or information, then it's strictly nominal. So always you have to, you the statistician, you should be able to know. And all these things we're talking about, someone will ask, what's the essence? What's the essence of, first of all, knowing qualitative variables and qualitative variables? We are going to learn very soon that the type of variable would actually determine the type of statistical test you can perform. And we also learn that when we start the regression analysis, we will find out that even the qualitative variables, I forgot to tell you that qualitative variables too, we have two distinct types of quantitative variables, sorry. For quantitative variable, we have two distinct types, okay? We have discrete, and then we have continuous variables, okay? So keep in mind that the numerical variables, those variables that naturally take up numbers, height, if I ask you what is your height, you give me a number. If I ask you what is your age, you give me a number, okay? But one thing I want you to keep in mind is that all numerical variables or quantitative variables can be categorized into two. We have discrete variables and we have continuous variables. Now, the difference is that for the discrete variable, they can never be fractional, or they can never be decimal, or they cannot take fractional values. So right now, if I ask you what is your the number of chairs in your room, you won't tell me you have 2.5 chairs, and that makes it a discrete variable, okay? If I ask you how many people actually died from COVID-19 in Ghana, you cannot tell me maybe 720.5. No, it doesn't work that way. You get what I mean? So in that case, it makes them not. So anytime you hear a variable, number of anything, number of something can never take a decimal value. So it makes it discrete. Now, keep in mind that for continuous variables, they can take up decimal. So you can actually measure someone's height and get maybe 2.5 something meters. You can actually get 2.1 meters. You get what I mean? So that's the difference. I mean, that's just the, let's say, the layman difference between discrete and continuous variables. When you start with the statistical modeling, you find out that the type of numerical variable would also inform the type of statistics you can do on it. So they are very useful. They are useful information you need to know. All right. Now, I'm just going to talk about data structure, because you are going to do data analysis. You are going to talk about data analysis. It will make sense to have a fair idea. First of all, how should you restructure your data? There are so many people, especially those who are not very statistical, who might be interested in doing research. And sometimes they don't even know how to even restructure their data. Now, keep in mind that Excel is very useful to summarize your data, okay? If you are using even programming languages and other softwares, which we'll talk about later, so you find out that Excel actually is very useful. Now, as you can see from this, you realize that the variable headings are always the first row. If you look at table 1, the variable heading is the first row. Table 3, the variable headings are the first row. So we have observation, we have I, we have T, we have medal rates. So that's the variable headings. Then the actual data actually comes down, isn't it? So technically, that is how you should always restructure your data in Excel. Okay. So in Excel, when you have your data structured in Excel, you can easily import it into any programming software. Okay. And this is how you should always structure your data. And don't have multiple Excel sheets when you're working with a programming, any form of statistical software. Don't. So what I'm trying to imply is that suppose you created, let's say, 3 different Excel sheets, one Excel, but you have 3 different sheets within the Excel, and you are importing it into, let's say, R or a programming software, you might be getting errors. Okay, so it's always advisable that one single data should occupy only one Excel file. Okay, and then when you're importing in some softwares, you might change the extension of the Excel to something called CSV. We'll talk about that later on, and tomorrow too, we'll learn about that as well. But I just want you to keep in mind that always when you are entering or restructuring your data, always the first row should be the variable names or the variable headings, okay? Then each other row becomes data for your subject. Okay, now we have so many types of data. We've already talked about different types of variables. So here you realize that each column or the column headings So this is the first column, individual. This is the next column, and so on. Now, each column can either be qualitative or quantitative, okay? Each column can either be quantitative or qualitative. So anytime, but it doesn't mean that, so for instance, if you look at this variable, female, you realize that they've written 1 and 0. It doesn't mean that female is now quantitative. That's why I said that assigning numbers to categorical variables or quantitative variables, actually that doesn't make them what? Qualitative. But what they do is that it only helps us to actually do analysis with them, okay? So we call these dummy variables. Assigning zeros and ones is dummy variables. You can use 1 and 2s. You can even use 3 and 4. All you have to tell them is that 3 means males and 4 means females, and you are good to go. Now, we have different types of data structure. Each data structure would also inform the kind of statistical test you can do. And I should have told you earlier that this meeting is being recorded, and then it will be uploaded on YouTube as well, especially the statistical bit. So don't worry when I'm going a bit fast, because we don't have too much time. And you can always watch the YouTube video at your own pace. I mean, I will talk in depth about that as well. So let's proceed. So we have different types of data structure. The first one is cross-sectional data. Now, what is a cross-sectional data? So cross-sectional data is simply a data that we collect at one time point. So suppose you are collecting data within a year. So this one, they collected data within a year, and the year was 1990. It doesn't mean that they collected all these data in 1990. It doesn't mean that they collected it at a particular day. It could be different days, but their whole focus was that within a year. So if it's within a year, it doesn't matter when you collected it. Once it's within a year, it still makes it what? Cross-sectional. So the focus of cross-sectional data is that for cross-sectional data, we collect data across different subjects within one time, or within a year, or within a single time point, okay? So it could be within a day, it could be within a week, it could be within a year, whatever you want, okay? So that's cross-sectional. And look at this. For cross-sectional data, each single row corresponds to one subject. What I mean by one subject is, I don't want to use one human, because it's not always that your experimental units or observations or subjects will be humans. You could have inanimate objects as well. Okay, so it could be fish, it could be chairs, it could be anything depending on what you are interested in studying. But predominantly, it could be humans. So for cross-sectional data, I want you to keep in mind that every single row corresponds to only one unit, or sorry, only one individual. Every single row. An individual cannot have more than one row for cross-sectional data. So that is one thing I want you to keep in mind. And most of the regression models that you are going to fit, there are most instances, you should be able to know that if the data is cross-sectional and the data is either pooled cross-sectional, which I'm going to talk about it, and panel data, we analyze them differently. So for cross-sectional data, I just want you to know the difference, that for cross-sectional data, every single row corresponds to only one subject. Every single row. So if you have 10 rows, 100 rows in this case, it meant the study participants were 100. That's what it implies for cross-sectional. Now there are instances where it's still cross-sectional, but what happened was, so if you look at this one, when you talk about the pooled cross-sectional, look at the difference between the cross-sectional and the pool. Look at the years. For this one, all the subject data were collected in 1990. Now for this one, imagine there are instances where you are collecting data, you are interested in collecting data, right? But the data you are collecting for each subject, like I told you for cross-sectional, every single subject should have only one record. That is one row. But there are instances, maybe you collected, let's say, data on first 100 people in 1990. And then in another year, which is 1991, you also collected information about other different individuals. So you realize that it's like each individual's data was collected at one time point, isn't it? However, not all the subjects had their data collected at the same time. That's basically what the pooled cross-sectional implies. So the word cross-sectional implies that each subject has only one record of data, okay? And the cross-sectional also implies collecting more than one variable or one information at a time, okay, at one single. So you realize that for all these cases, all these are in a way cross-sectional. Table 3, table 2, the data there are all cross-sectional. Why? Because we have more than one variable or information, okay? However, what distinguishes between these three, first of all, is that for this one, every single subject has only what? One data records, and all the data were collected within the same time period. But when you look at table 2, it's technically the same as the cross-sectional data, which is technically the same thing, but the difference is that not all the subjects had their data collected in the same year, okay? But each subject had only one record of data. Are we okay with the difference between the pooled and cross-sectional and then the cross-sectional data? Now, when you talk about panel data, aka longitudinal data, this is very useful data that we usually collect. And what people do statistically erroneously, or the mistake people have been doing is that they've been using models for cross-sectional, for panel data. And a lot of people don't know how to even analyze longitudinal data. And longitudinal data are data which are naturally observed in reality. How? So look at now for the longitudinal data, you realize that for the first 2 rows, this one corresponds to subject I. Subject 1, the first 2 is for subject 1. If you remember for the cross-sectional and then the pooled cross-sectional, each subject can only have 1 row, meaning that each subject can only have 1 record of data. But with the longitudinal, situations where we are actually collecting information about each subject over time. So meaning that if I consider one particular subject, I'm collecting maybe your information yearly, maybe in 10 years, I'm collecting your information every year. I went and record. It's like those follow-up studies. And if you look at COVID-19 vaccine efficacy, you realize that they will consider some subjects. And after considering the subject, they'll be measuring some variables. Okay, they will measure maybe their blood pressure. They'll be measuring certain things. Okay, temperature and other things. It makes it cross-sectional. But they'll be taking this measurement over time. And taking this measurement over time means that for each subject, we would have more than 1 record for each subject, okay? When if I say more than 1 record in the context of data means that a particular subject can have more than one row. One subject could have 5 rows, and it doesn't mean that all the number of time points will be the same for each instance, okay? Meaning that some subjects could have, let's say, data for 5 time points. Others could have more than 5 time points, it doesn't matter. But once you have a data like that, is what? Panel data or longitudinal data. If you want to do any form of regression, keep in mind that if you use a regression model or any statistical test or any statistical models for cross-sectional, rather for panel, everything you've done is wrong. And one thing we have to note is that for the statistical softwares, they will do what you tell them to do. So getting output from statistical softwares doesn't mean you are doing the right thing. You can actually be doing the wrong thing, but get a very nice result. Okay, so keep in mind, so knowing the type of variable, knowing the kind of data structure you are working with should also inform the kind of statistical analysis you can do with them. Okay, and we have one also common one that we call time series data. And so for the time series data is basically collecting, let's say, so the time series data the data is collected at only one. So for instance, we are collecting, let's say, maybe COVID-19 cases every day, daily. So if I record the number of COVID-19 cases in Ghana, let's say the number of recovered cases, okay, or let's say the infected cases, and I'm recording it every day, then in that case, we are going to have a daily data, okay? And you realize that with that, I'm not following up on any single individual. It's just one. So it means that for the panel data, when we consider each individual's data is a time series. For the panel data, when you consider each individual's data is a time series. And then, so meaning that panel data is actually a combination of cross-sectional data and time series data. Because we said that for the time series data, we are collecting information about a single subject or a single variable over time. But the very moment we consider more than one subject while doing that over time, that makes it panel. Okay, so panel data is technically a combination of cross-sectional and time series data. All right, and like I said, the different structures would inform different kind of statistical analysis you can do, and be very careful not to use a model that only works for cross-sectional data for panel. Okay, But whatever model that works for the panel data would also work for the could also work for the pooled cross-sectional for some reason, which I will explain because of the time in there. But let's continue. Okay, so now the next thing, so first of all, we've already, just to wrap up, we've already talked about a bit descriptive about statistics. We've already talked about the kind of variables we have, and we said we should be very careful that we have two types of variables. We have numerical or quantitative, and we have categorical and what? Or categorical or qualitative. And we said that assigning numbers to categorical variables do not make them quantitative, okay? It only makes them useful for us to be able to do further analysis with them. That's why we assign those dummy variables. Now, one thing we have to keep in mind, I also made mention that every statistical test, we have the parametric and non-parametric version. And I also told you that every statistical model, we have the parametric and non-parametric version. Just that for the models, we have a semi-parametric instances, okay, which I will explain what type of model could be semi, okay, I will explain. But if I want to go in depth with what is the difference between non-parametric model and then parametric model, you find out that for the parametric models, we have finite number of parameters that we want to estimate. So if you take a typical regression model, for instance, and let's say I have 5 independent or 5 predictor variables that I want to see how they influence a certain dependent variable, okay? Let's say I want to know some 5 variables, how they affect maybe inflation in a country, how they affect maybe recovery, maybe recovery or whatever. So in that case, what I'm trying to imply is that in a classical regression, the number of, if you have 5 independent variables, automatically each independent variable will have its own parameters, okay? Each independent variable, if you have 5, would have its own parameter, okay? And so at the end of the day, 5 independent variable implies we have 5 parameters, just that there's always something we call a constant that we add to it, making it 6. So I just want you to keep in mind that always for parametric models, we can actually count how many parameters we are trying to estimate. But for non-parametric models, it has infinite number of parameters. So for non-parametric models, they are actually instances where you cannot actually estimate all the parameters, or you cannot know all the parameters, or you cannot count them. They could be infinite. So just keep in mind that that is actually the statistical difference between parametric and non-parametric. But the term parametric actually implies that if we are talking about statistical tests or statistical models, and we are talking about it being a parametric method, parametric methods, they have strong and specific assumptions that needs to be met. So that's what distinguishes also. So we have different ways of distinguishing what a parametric test is and non-parametric test is, what a parametric model is and non-parametric model is. Anytime you hear the word parametric, it implies that we have some strong and specific assumptions that you need to meet before you can use them. So you don't just say, I want to do Anova, because you've seen people using Anova to compare means across more than 3 groups. You should, more than 2 groups, 3 or more. You should be able to satisfy some conditions because it's a parametric test. So just keep in mind that if you want to, so it doesn't matter whether in your school they are not too much into statistics, but for some reason you might want to publish your work. So it's always good to do the right thing. And what I'm saying is that if we are sticking to a parametric method, whether being parametric model or non-parametric model, okay, what I'm saying is that there are some specific, strong and specific assumptions that needs to be met or satisfied. If you know that you are not interested in satisfying those conditions, go for non-parametric tests. Because non-parametric tests, they are robust to statistical assumptions, and they are also have weak and then non-specified assumptions. So it means that for non-parametric tests, if you don't want to worry more about what assumptions, you go for non-parametric tests. However, if parametric tests are actually, if the parametric assumptions are met, parametric models will always do better than the non-parametric test. So keep in mind that if parametric assumptions are met, parametric tests will do better than non-parametric tests, and parametric models will do better than non-parametric models if the parametric assumptions are met. But if parametric assumptions are violated, then you can clearly see that the reverse will happen. Okay, so technically the non-parametric tests and non-parametric models are more robust to assumptions. Okay, fine. Now I'm just going to elaborate on just few statistical tests we can do. And then I want you to also keep in mind that we have different type of statistical tests you can actually do. Okay, so now I'm just talking about statistical tests. I'm not talking about statistical models. So what I'm talking about is statistical tests. So we shouldn't confuse statistical tests with statistical models. Okay, so in most of your studies, irrespective of the field you find yourself, you come at a point where you'll be comparing means across groups. Okay, so keep in mind that if you want to, so like I said, if you want to do statistical tests, okay, so now I'm not talking about models at the moment. So if you want to do statistical tests, I said we have parametric test and non-parametric test. Every parametric test has its equivalent non-parametric version. That is also one thing I want you to keep in mind. Every parametric test has its non-parametric version. Now, if you are comparing, let's say, means across groups, the first thing we usually think about, so you should know the various types of mean comparisons or the various types of mean tests and know when to use a particular one. So you shouldn't be confused. At this point, by the end of this study, you shouldn't ask someone, oh, I want to do a mean comparison test. This is the kind of data I have. What test do you think I should do? You should be able to tell me. Now, when you talk about pair t-test, so pair t-test is basically when you're, so for instance, let's say for each individual, I recorded, let's say, your temperature before I gave you, let's say, some vaccine, and I also recorded your temperature after I gave you a vaccine. So you realize that for each individual, we have, let's say, 2 measurements, and then the 2 measurements are coming from the same individual. And suppose we now consider more than one individual, meaning that we consider, let's say 30 individuals, where we have records, their measurement, their temperature measurements before I gave them maybe some form of intervention, and after I gave them some form of intervention. When you have such instance, okay, that is when we want to compare the means between those two groups parametrically. That is when we use the pair t-test. Why? Because the 2 measurements are still coming from the same individual. So it makes the 2 measurements dependent on each other. Are we okay? But it only becomes independent when I consider 2 different groups of individuals. So let's say I measure temperature of, let's say, some 20 individuals, and I consider a different 20 set of individuals, and I measure their temperature, and I'm comparing the 2. Or maybe I take some females, okay, and those females, I consider another set of females, and I measure, let's say, their BMI, and I measure the body mass index for the first group, the body mass index for the second group. Because the body mass index is not coming from the same individual, and don't say that because the 2 groups are both females, so females means that they are dependent. No. What we mean by dependent implies situations where you took measurement of a subject before and after some intervention. In that case, those 2 measurements becomes dependent. And it's not always that the measurement will just be 2 measurements. There are instances you took more than 2. And that is where repeated measures actually comes in, okay? So keep in mind that anytime it's just strictly 2 measurements you took from a single individual, and you did that across several individuals, and you want to compare their means parametrically, we actually use the pair t-test. Independent t-test comes in when you're comparing means between 2 independent groups. Now, I'll talk about the Bonferroni pairwise test. Let me talk about the repeated measures. Okay. Anova here. So for the Anova is just an extension of the independent t-test. As I said, the independent t-test is comparing means between strictly two independent groups. And then the Anova is comparing means between more than 2. Okay, so meaning that if you have 3 or more groups and you're comparing their means, okay, statistically, and you want to check whether there's any significant difference in their means, in that case, you go for Anova. Now, whenever Anova is significant, there's a further statistical test we do, okay? Because if the Anova is significant, the next thing you would want to do is to now check, suppose there were 3 groups, and Anova concluded that, oh, there's significant mean difference in those 3 groups. The next thing you are interested in finding is that for group 1, is there any significant difference between group 1 and group 2? Is there any significant difference between group 1 and group 3? That is where the pairwise comparison test also comes in. And for the pairwise comparison test, I only mentioned one here. I mentioned Bonferroni pairwise test. But for in the parametric context, Bonferroni is good enough, but there's also something called 2K comparison. And for 2K, it has a limitation. The limitation is that when you're actually doing a multiple comparison with 2K test, we expect the for each group to have the same number of subjects or the same number of sample size for each group, or else you are going to get very unbiased, very biased results. Okay, but if you are not too sure, or if the number of groups are not the same, you can still go in for Bonferroni. Even if the groups are still the same, you can still go for Bonferroni pairwise test within the context of parametric test. And then the repeated measures ANOVA is just an extension of the pair t-test, whilst the ANOVA is the extension of the independent t-test. So I should have just say independent ANOVA. I mean, just to say that for ANOVA, we are comparing the means across more than 2 independent groups. But for repeated measures, where situations where you collected or recorded information about of a subject about more than one time point or more than one time, okay, so you have temperature, you took first temperature reading, you took another temperature reading, and you took another temperature reading, and you want to compare the means. Please don't make a mistake to find the averages of each of the or the averages of the 3 time points to represent the data, and then tell me that you are going to use maybe independent t-test or whatever for them. No, you should be able to, since the data was actually collected at, let's say, 3 time points or more, okay, and you still want to compare the means between 2 or more groups, between 2 or more, of course. So for repeated measures ANOVA, even if the groups are 2, okay, but you collected information more than 2 times, you can stick to repeated measure ANOVA, okay? So 2 or more, but you collected their information more than 2 time points. But if they are just 2 groups and you collected their information at just two instances, that is where the pair t-test comes in, okay? And then we know what the repeated measures is now doing. It's just an extension of the pair t-test. Now there are instances where you are comparing, let's say, means. Let's say I'm comparing inflation rate, the mean inflation rate across, let's say, countries in Africa. So you realize that there are more than 2 countries in Africa. So it implies that suppose I even make it between the regions of Africa, maybe West Africa, East Africa, North and South. Suppose I'm comparing, those are the 4 groups. I'm trying to compare their average inflation, okay, across those 4 groups. Classically, we can stick to the ANOVA, isn't it? Because there are 4 independent groups, okay, and then we are comparing their mean inflation. But what about situations where you have more than 1 variable you want to compare their means? Let's say you have you don't have only inflation, you also want to compare exchange rates. You also want to compare monetary policy rates. Maybe you also want to compare interest rates at the same time. Keep in mind that doing different or separate ANOVA for each of them will lose some form of degrees of freedom. Anytime you do a statistical test, you lose degrees of freedom, okay? So keep in mind that, and you don't want to lose a lot of degrees of freedom. That's why it's always, and I wouldn't want to say we are being economical here, but keep in mind that if we're able to do several tests at the same time, you get a better power in terms of the power of the test. So what I'm trying to imply is that if we want to now compare the means of, let's say, the mean inflation rate across those 4 divisions of Africa, and then you are comparing exchange rates, maybe interest rates, do them together. And that is where the MANOVA comes in. So MANOVA is multivariate ANOVA. So this is the first time you are hearing the term multivariate. Let me clarify the difference between, Gilbert, what's the time now? Just want to be sure the time now, so that.
It's currently 8:11 here. It's 8:11 here. So that means it should be 12:11 at your place. And
okay,
so I think we have about 8 minutes more. 8 minutes more for you to wrap up. Yeah.
Oh, then I have to run. Okay. If that's the case, then let me run quickly. So keep in mind that for this parametric test, your data should be normally distributed. If your data is not normally distributed and you do a mean test, you are going to get very wrong results. Why? Because the mean is affected by outliers. You all will agree with me that outliers are just extreme values. Okay, so suppose I have 3 data points, let's say 1, 2, 3, and I find the mean. And suppose the 1, 2, 3, I replace the 3 by, let's say, 100, and I find the mean. You can clearly see that when I replace it by 100, the mean value will increase towards the value, or the mean value will increase, isn't it? But if I want to find the median, if it's 1, 2, 3, and I increase the 3 to 100, still the median will be the middle number, which is 2. So the median is not affected by outliers, but the mean is affected by outliers, okay? So keep in mind that in order to use the parametric test, all these parametric tests I mentioned about the mean test, the first thing you have to test is your data normally distributed? And people have been making this mistake. They say that when your data set is 30 or more, it means it's normally distributed. It's never true. That 30 or more technically goes for the central limit theorem. That is actually the distribution of the sampling distribution of the mean, okay? So don't confuse the sampling distribution of the mean for central limit theorem for the data itself. So a data which has 30 or more sample size is not normal. You cannot conclude it's normal. The normality is about the sampling distribution of the mean or the test statistic of the mean that you'll be using. Okay, so just keep that in mind. Okay, fine. So technically, if the sample size, if the data is 30 or more, you can actually use these parametric tests as well. Anyway, but I just wanted you to keep in mind that if the data set is 30 or more, doesn't mean the data itself is normal. It's not true. But keep in mind that for the parametric test, your data set should be large enough, or your data set should be normally distributed. Yeah, okay, so those are the conditions. But situations where the data is not normally distributed, I said comparing means would result in misleading information or misleading conclusion. So in that case, we compare medians. You see the non-parametric tests I've written. Each particular test, the position of each test is the non-parametric version of the parametric test here. So the pair t-test, its non-parametric version is the Wilkinson sign test. The independent t-test, its non-parametric version is the Mann-Whitney test. So it means that situation where you wanted to compare means between two independent groups, and you found out that the data was not normally distributed, don't force yourself to use independent t-test. You can still use Mann-Whitney test and still arrive at the same conclusion you would have arrived. But in this case, you have a statistical backing behind your conclusion. So keep in mind that if the data is not normally distributed, comparing medians makes sense because the median is not affected by outliers. And then for Anova, the non-parametric version is Kruskal-Wallis. And for the pairwise comparison, the non-parametric version, for instance, Benforoni non-parametric version, we call Benforoni dance test, okay? And then the repeated measures Anova. So don't force yourself if you collected data of individual at more than 3 time points, and then the data itself was not normally distributed. You can stick to Friedman's test, which is the non-parametric version of the repeated measures ANOVA. And then MANOVA, which is doing multiple ANOVA, is its non-parametric version is multivariate Kruskal-Wallis test, okay? And then we have several tests. We have tests for proportions and correlations as well. And then so this is actually, I think, the last but one. So I just wanted you to keep in mind that we have lot of mathematical and statistical models, and then regression model is one particular branch set of models that you'll be using a lot in your studies. So anytime you're interested in looking at the linear effect or relationship of some predictors or some set of variables on a certain dependent variable, and keep in mind in this case too, in the context of regression, when we say univariate regression, it means that you have only one dependent variable. But at the very moment you hear something called multivariate regression, it means we have more than 2 dependent variables. So meaning that you can actually have a regression model where you have more than 2 dependent variables at the same time. But when you hear the term multiple, so there are instances you hear the word multiple linear regression. When you hear the word multiple linear regression, it doesn't mean that the dependent variable has more than 2 the dependent variable has more than 2 variables. No, multiple linear regression simply means that the independent variables were more than 1. When the independent variable is just 1, we call it simple. So if you hear simple regression, it means the independent variable is 1. So I can actually have a multivariate simple regression, meaning that I had more than 1 dependent variable, but only 1 independent variable. So it makes it multivariate simple regression. The very moment I call it bivariate simple regression, it means we had only 2 dependent variables. Trivariate means we had only 3 dependent variables. And then more than 3, we can say that multivariate, okay? And even 2, you can conclude on multivariate. So keep in mind that multivariate in the context of regression means several dependent variables, whilst multiple means several independent variables. And simple means that only 1 independent variable, okay? And here we have so many classes of regression models. So we have something we call generalized linear model, okay? You get the recording of this, so don't worry, you don't have to memorize everything. Now keep in mind that the nature of the dependent variable, the nature of the dependent variable and the nature of the data informs the kind of regression model you can use. So these are the two most important things in order to conclude on the type of regression model you can use. The nature of the dependent variable and also the nature of the data you are working with. If the data is cross-sectional, we have a class of, so if the data is cross-sectional, all these class of models will fit into a cross-sectional data. The first one, if the data is cross-sectional. If the data is panel, whether pooled cross-sectional or panel, you can, it will go into the generalized linear mixed model. What I will explain a little bit further. So keep in mind that the nature of the dependent variable indicates the type of regression and also the nature of the data anyway. But the dependent variable is the key thing here. So if the dependent variable is continuous, you can use the OLS regression. If the dependent variable is categorical, that is where you use logistic regression. So here I was supposed to say multinomial, binomial, and multinomial logistic regression. So if you hear the word logistic, it means that the dependent variable is categorical. But when the dependent variable has only two levels or two categories, we call it binomial logistic regression or binary logistic. But if it has more than two categories, then we call it multinomial. Now, Poisson regression, quasi-Poisson regression, and negative binomial regression are used in instances where the dependent variable is discrete. Because I told you that when the dependent variable is, the nature of the dependent variable informs the type of model. So if you are looking at factors influencing the number of road accidents in Ghana and you use OLS regression, you are wrong, because the dependent variable is what? It is discrete. So you have to use Poisson regression, and Poisson regression has an assumption, and that, because I told you that all these are parametric models and we have to satisfy some specific assumption. Poisson regression has an assumption that the mean of the dependent variable and its variance should be equal. If it's not equal, it means there's something called dispersion in the data. If there's dispersion in the data, it can lead to wrong conclusion. So in such instance, the quasi-Poisson and the negative binomial regression actually becomes useful when there's dispersion in that data. The generalized linear mixed model are suited when you have a panel data. So with this one, what we do is that the independent variables of interest are what we call the fixed effect variables or the fixed effect, and then all sources of replication. So don't forget that if it's panel, there was replication in time, then time becomes something called random effect. Anything that adds additional randomness to the data, it could be randomness due to time, repetition in time, or it could be repetition in space. Suppose you collected data across some locations over time. Those locations can contribute to something called spatial pseudo replication or spatial replication. In that case, when you're fitting the model, you should be able to account for all those sources of replication, whether in space or in time, by adding them as something called random effect, okay? So, and then the independent variables of interest becomes your fixed effect. So that's basically what the mixed model does. So meaning that not all your variables will be considered as variable independent variables of interest, or not all the variables will be considered as fixed effect, but those that causes additional sources of replication, be it temporal replication, that is repetition in time, or repetition in space, actually forms your random effect. Now, the generalized additive model is actually, Gilbert, can I get a little extension, because we didn't technically start exactly on
yes,
at 11.
Yeah,
so
I
what's
think
the
we
time?
can give you. Yeah, it's now 8:20. We can give you like 6 minutes more.
Okay, 6 minutes should be fine. I'll wrap up. Okay, so keep in mind that all these regression models we are actually using, okay, is a linear model. What we are saying is that we are trying to predict the linear effect of some predictors on the dependent variable. But there are instances where not every variable might have a linear relationship with the dependent. Let's look at COVID-19. If you look at COVID-19, for instance, we said that children or those who have low age or like children, for instance, they were less likely to get the infection, isn't it? And then those within like people like us, I mean, those in the middle age group were also literally less likely to get the infection, right? But the children were more or less likely than the middle group comes, and then the aged were more likely. In that case, it's a typical linear relationship in terms of prevalence. So it means that age in that case have a linear relationship with the prevalence of COVID, isn't it? But situations where we have a disease like malaria, which can affect more children and also affect the aged more than those of us in the middle group, in that case, it has a non-linear relationship. So if you probably do a scatter plot, okay, you might not find a linear trend in such a data in terms of comparing age with the prevalence. So in that case, we use something called additive model. With the additive model, those variables that do not have explicitly linear relationship with the dependent, because The linear models is assuming that each variable should have a linear relationship with the dependent, be it GLMs or the GLMs or the linear and the mixed models. Okay, it's assuming that the dependent variable, the independent variables have a linear relationship with the dependent. But is it always so? Because there are instances where some variables will have non-linear relationship. So what the additive model does is that it fits something called splines to those variables that do not have a linear relationship with the dependent. Fitting splines is a way of trying to smoothen those variables so that we would be able to get something relatively linear. Okay, so that's all what the additive model. So it's not doing anything much different from the GLM. The only thing is that some variables will not be entered into the model as it was. We would have to do some transformation by fitting splines to them in order to make them almost linear with the dependent, because we want to make linear prediction, isn't it? And then we have some class of models, which a lot of you might not be aware. We call it machine learning algorithms. An example of these machine learning algorithms are classification tree, random forest, gradient boosting machines. We have extreme boosting machines. You can read on them and keep in mind that the machine learning algorithms, we have one for time series modeling. We have any model, all the parametric models. It appears that we have 8 machine learning algorithms that can equally do better. And the machine learning algorithms are supervised and sometimes unsupervised learning. So they pick your data and then they're able to learn a lot from the data than sometimes most of these parametric methods. So it's something you should also think about. And then keep in mind that when you're fitting a regression, not all the variables will be considered in the model. So how do we select variables that are supposed to be entered into the model? So we have something we call variable selection techniques. These are always the first thing you need to do before you fit any regression model. So we have stepwise regression, we have penalized regression methods, and we have recursive feature selection. Okay, now beware of multiculinarity. So multiculinarity is that when you're fitting regression models, we don't expect high correlation to exist among the predictors. We want high correlation to exist between the independent variable and the dependent, but not among the predictors. If there's high correlation among the predictors, what happens is that it causes multiculinarity. What are the effects of multiculinarity? You find out that there are instances where your overall model is significant, but none of your independent variable was significant. Technically, if one of your independent variable, at least one of your independent variable is significant, then we expect the overall model to be significant. But situations where the overall model is significant, but none of your independent variable is significant, or at least one of your independent variable is significant, but the overall model is insignificant, then it means that there was multiculinarity. And in that instances, it meant that you have to deal with the multiculinarity by eliminating those variables that causes or contribute to those multiculinarity. Meaning that variables that are highly correlated with each other, we can take them out, or we can take one of them out. How do we do that? How do we know those who are having high correlation? We can compute something called variance inflation factor or something called tolerance. They are good measures. And if we have high multiculinarity, almost all these models, all the first 3 will not hold, okay? But if the first 3 doesn't hold, the penalized regression models actually comes in. They are suited to situations where we have high multiculinarity in the data. You can equally use the penalized regression models, okay, to still fit such data with high multiculinarity. So it doesn't mean that if there's high multiculinarity, throw away, don't do your regression. We have other things that can equally deal with that. Ridge regression, lasso regression, elastic net, and we even have another class of model called envelope-based models. All right, so now this is the last thing. So about the statistical softwares that can be used for data analysis. Keep in mind that we have the SPSS, Stata, eViews, Minitab, but keep in mind Stata and eViews are more useful for econometric modeling. Those who have been doing regression or those who are doing a lot of time series analysis, Stata and eViews are very useful, and Minitab can also be useful in that sense. So Gretel is also another statistical software, and Excel Stat is also a statistical software. But you see, I classify all these into as one group. Why? Because they are not programming languages. Okay, so all these are statistical softwares, but they are not programming languages. Even though Stata, you can program within Stata, doesn't mean that it's a programming language, okay? Because it was built on other languages, so it's not a programming language. R is, to me, that's actually, so R and Python so far are the most, let me say, the most popular statistical softwares that is in the market. So these 2 are dominating the data science market, okay? So R and Python. And then R is what I have expertise in both R and Python, but R is my first language, and then Python is my second. And now I am interested in Julia, and I'm also using Julia. The reason is because Julia is faster if you want to look at the programming languages, Julia and C, both C and C++, Julia is as fast as C. So what the statistician did was they knew that R is very powerful in terms of statistics. So R is specifically for statistical analysis, and Python can be used for statistical analysis, but it's usually useful for numerical analysis, especially those in the pure math field. But for R, you can also use it for the numerical analysis, but it has extra packages for any statistical test you want to do that you might not find in Python. But for Python, if you want to do any numerical analysis, you are confident and you want to do something called symbolic programming. I mean, sometimes you want to integrate. You don't want to, if you don't even know how to integrate manually, the software can do the integration for you. That's what we call symbolic programming, okay? So Python can do that. R can do that, but sometimes it needs a little bit additional effort, but Python will do that with ease. But Julia combines the capability of R and Python, and it's also faster than R and Python. So when you are programming in Julia, the syntax is not different from Python and R. They are similar, but the additional advantage is that this is much more faster. SAS is also useful, but technically it's also a programming language, but R dominates it. MATLAB is a semi-programming language. It's not technically a programming language per se, but it's a semi-programming language, and it's a debate that people have been fighting over whether we should classify MATLAB as a programming language or not. But these are just few statistical softwares. But for tomorrow, we'll be using R. And the reason why we are using R is because as far as statistics, I can prove to you that R is technically the best among all of them. But for the Julia, it's useful when you need to add additional speed, okay? Of course, when some of your models are very complicated so that it takes a lot of time, there's something called parallelizing your codes. You can parallelize your codes to run on multiple cores. At the moment, if you run any analysis on any software, it's using a single core on your computer. But when you parallelize your codes, it's able to run on multiple cores. But Julia actually is much faster, even without parallelization. And you can imagine after you parallelize your codes, what will happen, okay? So I will end here because of time. And then tomorrow, we are going to stick to, we are going to do one of these regression analysis, and then learn a little bit of some of the inferential statistics that I mentioned. And just to recap, keep in mind that I already started a form of initiative. Okay, so I'm done with the talk. This is just a little announcement. So I already started an initiative where I wanted to actually improve or motivate mathematical programming among students from Africa. I initially thought of only Ghanaians, but later on I realized that I needed to add all other African countries. And then not just Africans, anyone was also allowed to join. So, and then, so we usually meet on Saturdays? Okay, Saturdays at 4 p.m. GMT.
Saturdays.
Yeah, and then every meeting is recorded on YouTube. You don't necessarily have to force yourself to join the meeting because of your time and the time difference. But every meeting is pre-recorded on YouTube. It's done on Zoom, but recorded and posted on YouTube. Okay, so you can watch at your own pace. And so meaning that there are a lot of things that I might not, especially tomorrow when you are doing the statistical analysis, I'll go straight into the inferential statistics. There are a lot of things I won't waste time on because we've already done that from scratch in R from scratch, and everything is on YouTube. And so tomorrow I'll make sure you get the links, and then those who want to join the class officially to learn, and it's free, you don't pay anything. It's just an initiative that I'm doing from my own free will. So I will end here and see you tomorrow as well. If anyone has a question, you can just shout, and yeah, thank you.
Yeah, thank you very much. Thank you very much, Clement.
Thank you.
Yeah, before the moderator comes in, we want to acknowledge some protocols in our midst. Sorry. Yeah, so we have former presidents in our midst. His name is Mr. Ben Baffo. Yeah, he's a current PhD student at Shanghai Maritime University. We also have the NUGS president, NUGS-CHINA president in our midst, with his secretary as well, Miss Francisca Abo. Yeah, sorry, the NUGS president's name is Mr. Collins. Yeah. And then all protocols duly observed. Yeah, I cannot mention everyone's name. We also have our own president, NUGS-Shanghai, Mr. Thompson, Anu in our midst. Yeah, so please forgive me. I can't mention all names, all protocols duly observed. Yeah. Ms. Tina, please take over. Yeah, thank you.
Okay, thank you so much, Honorable Gilbert. Honorable Clement, please, do you have something to say?
Yeah, I was saying that if anyone had just one or two, I could just take one or two questions.
Yeah, sure. Okay, so we want to take some questions. So I've seen Irajua, yeah, please unmute yourself and ask your question.
Okay, thank you very much. Thank you, Clement, for your presentation. Well done. So I have a couple of questions. So you talked about some statistical techniques. My question is, what if you want to do some qualitative work? Okay, let's say you have a
Please
topic.
put on your video. Please. Sorry for interrupting. Could you please put on your video so we can see?
Pardon me, I'll
we
turn on my
thank all people joining us around the world, from Russia, from Nigeria, from everywhere, UK, Ghana. Yeah, we thank everyone. Yeah, please go ahead. Sorry for the interruption.
Just a second, I have to dress a little bit properly.
Oh, Gilbert, I think she can just go ahead. Maybe she's not properly.
Yeah, please go ahead.
Okay. Sorry about that. Next time I'll make sure I'm properly dressed for this event.
Oh, no worries.
Okay, so back to my question. So what if you want to do a qualitative study, okay? But then from your analysis, okay, from what you're thinking, okay, maybe these things you've talked about, but you see that in your analysis, you can make use of like Anova, okay? So maybe you want to analyze maybe 2 or more variables, okay? So do you have to stick to this statistical analysis, or you have to go strictly to the qualitative analysis?
Yeah. Let me help you with the question. So basically, the question she's trying to imply is that, you see, there are instances where you are doing a qualitative study, but there are other instances you are adding the quantitative bit. So in that case, what do we say? Keep in mind that we have mixed studies. So we can have purely qualitative studies where you are just transcribing tests and other things. And you could actually have purely quantitative studies. And you can actually have a mixed study, which is partly qualitative, partly quantitative. People can strictly work with qualitative, which is fine. Some fields, you cannot do anything quantitative apart from probably trying to summarize your study participants with respect to their age or some demographic information. But one thing I want you to keep in mind is that once you are doing Anova and other things in your study, it only makes it a mixed study, which is still legit, which is still accepted. So there's nothing wrong with that. Are we okay? Does it answer your question, please?
So just a follow-up question, okay?
Okay.
So I showed my work to one professor, and he was like, I should be specific on what I want to do. If I want to go qualitative, I should stick to qualitative, and if I want to do quantitative.
Yeah.
So I'm a bit confused. Let's say.
So what the professor said, which I disagree with him, is that you have to be specific in your methodology that you are working with mixed methods. So the very moment you say you are working with mixed methods, and you've also indicated that by mixed methods, it means that your statistical analysis will involve both qualitative and quantitative analysis, then you are good to go. So be emphatic means that don't say you were working with qualitative study and later on we see you are doing some quantitative bits. But if we are saying that you have some quantitative statistical analysis in there, the best thing you need to do is that state that you are working with a mixed study or you are doing mixed study, such that you are doing mixed study data analysis. So keep in mind, mixed study would just imply that your statistical analysis comprise of both quantitative and qualitative bits. Okay, so for the qualitative analysis, for those who are not aware of it, it's basically where maybe you interview some participants and afterwards you are trying to transcribe their responses in a test format. So with that, we don't technically use a statistical software for that. Okay, it's all about transcription or whatever. So we only use statistical softwares when you are dealing with quantitative studies. But the very moment you are doing any quantitative bit in your work, just state emphatically you are doing a mixed study, in brackets, both qualitative and quantitative analysis, and it should be fine. And there's nothing like strictly qualitative, strictly quantitative. You can do both. And usually when you do both, it even makes it more better or perfect than the individual qualitative or quantitative, because the qualitative will have its own advantages, okay? And then the qualitative has its own advantages. The mixture of the two actually becomes better. And then, yeah, so just a quick one, when I was talking about the panel regression, the panel data, and I said the generalized linear mixed model is useful. There's also another class of model called panel regression, which is also made strictly for panel data. So I forgot to add to the slide. So anyway, so any other question, I'm happy to take.
Okay, thank you very much. I think I'll see you personally for more insights.
No worries.
Okay, thank you so much, Irajua and Honorable Clement. So we have Louis Kofi. Please go ahead and ask your question.
Okay. Good evening, everyone. My question is about how relevant is Heteros Cadacity to regression analysis? Thank you.
Okay, so for that is relevant, but not always relevant, depending on the model you are working with. So keep in mind that when you are working with, let's say, OLS, okay, OLS regression where the dependent variable is continuous, and you are working with a cross-sectional data, okay, we expect that the residuals, okay, we expect that the variance within the residuals should be constant, okay. So that constant is what we mean by homoscedastic. But the situations where for each subject, the variance within the dependent variable, I mean, the variance technically is changing over time, or each subject will have a different variance. Then it means that it's heteroscedastic. In that case, the OLS regression will fail. But we have class of models that deals with that. Example is generalized least square regression. So that is where, so if you want to still do a GLM or a classical OLS regression, but the assumption of the homoscedastic assumption or the equal variance assumption between the groups are not met. Okay, in that case, if it's a regression you wanted to fit, you can actually go for the generalized least squares and it should be fine. And we even have another class of methods called partial least squares, which also can easily deal with homoscedastic instances where the residuals have no constant variance. Are we okay with that?
Yeah, very clear. Yeah. Okay. Thank you.
No worries.
Okay, please, any other questions? Okay, I think I saw some questions on the chat. Okay, so Osman was asking, how about hybrid quantitative and qualitative analysis? How about the variable for this kind of analysis?
Yeah, I think that the hybrid has just got to do with the mixed study we're literally talking about. So yeah, so that's studies which involves both the mixed. So it's similar to the question that I've forgotten the name. The question that the first question, not very difficult.
Okay, Rajwa asked.
Yes, please.
Okay, someone is also asking if there's any book or PDF file where we can learn about everything that has been taught today. So
okay, so technically you wouldn't get a single PDF that would summarize all the things I talked. Most of the things I talked were based on experience. You might not get a PDF that summarizes all these at the same time, but you can get access to the slide. But you can only get a PDF on, let's say, regression analysis. You can get a PDF on regression modeling, okay? But you cannot get a PDF which is doing regression modeling in details, and at the same time, we'll be talking about, let's say, basic statistics. It doesn't work that way. Or you cannot get a machine learning part, machine learning algorithms also within there. So you can have a whole PDF on machine learning algorithms, a whole PDF on regression analysis. And don't forget that when you talk about statistical models, it's not just regression. We have so many, we have even simulation models as well, which is predominantly what I do. Yeah, so I can try and get PDFs of relevant PDFs and share together with the slides, and then you can get it from me, and you can also get it from Gilbert as well.
Okay, thank you so much. So lastly, I would like to ask that you mentioned something about a class you've been having. So if anyone is interested, how do we join?
Okay, so basically, so like I said, it's a free class, and then I manage it completely on on what we call Piazza. So so you can take my email address. So I'm putting my email address in the chat. So once you send me an email address and just tell me you want to enroll, you are so and so, you want to enroll to the class. Because if you don't enroll, you will be able to watch all the YouTube videos, but you'll not be able to download all the R scripts and the data we've been using. We've done 6 different classes, meaning that we have 6 different scripts, and the kind of programming we're doing was a serious thing you won't get on YouTube. I mean, you won't get elsewhere, because most of the things, like I like to teach from experience, such that based on my personal experience, then I kind of educate or teach. So it makes you more, I think, better than trying to read a lot online. So my email is chumecc. I'm putting it in the chat at cardiff.ac.uk. So that is my email. I hope you can all have it. So
address?
that's my email address. So all you need to do is send me an email and just tell me you want to enroll. So I'll add you. So once you enroll, I'll send you a link in an email, and I'll also forward all the everything we've done also in a different email. And then you just enter some details on that Piazza link. And after entering your details on Piazza link, you'll be able to have full access to all the documents. Technically, once you are on it, you can actually have all access to all announcement, all assignment, everything. And then you can learn at your pace. And I'll be going on a little bit break over the Christmas period. So if you're able to join now, you'll be able to have a lot of time to actually catch up, so that next time if I continue, you'll not be all alone by yourself. So this is because I'll be breaking over the Christmas break. Technically, from next week I'll be breaking, and then but you can sign up and then start going through everything at your own pace. And trust me, you will learn a lot, because it's so interesting, and it's like it's something you wouldn't regret joining, and it's free as well. All right, thank you.
Okay, thank you so much, Honorable Clement Chumesi, for today, for such an insightful and educative presentation. We've learned so much. Thank you all for joining, and we'll see you tomorrow. Tomorrow we'll be talking about an introduction to data analysis using the R programming language. So thank you all, honorable members, for joining today's academic seminar. And thank you to Honorable Clement once again for your time. Thank you so much.
No worries, it's a pleasure.
Okay.
Yeah, hello. Thank you. Yeah, thank you
very
much.
Thank you very much. Thank you very much. Great class. Thank you so much.
Yeah.
I wish you all well.
Today is just a teaser. Tomorrow is going to be more fire. Yeah.
Hello, Honorable Gilbert.
Yes, please.
Yes, so I think since we are going to use the R software tomorrow, I sent a link, the Anaconda.
Okay.
I think that Anaconda has the R system installed in it, so it's free to download. So I think most of us should go there and download it prepare for tomorrow's class.
Anaconda, yeah. So for Anaconda, once they download Anaconda, they can easily install RStudio anyway. But there's a whole YouTube session, actually the C session, where within Anaconda there's also something called Jupyter Notebook. And it's a very powerful integrated development environment, or IDE, that can easily use to run R, so that you'll be able to see all your codes, your results, everything will be there, and you don't have to be creating separate folders to be saving all your scripts. It does everything for you. And then, so the C's YouTube video is technically, I showed how you run R on Jupyter Notebook. But when you watch the first YouTube video to the third, I was using RStudio. But afterwards, I switched to Jupyter Notebook, and then in the C's YouTube video, you find out that I was strictly teaching how to install Anaconda in the first place, and how to add R kernel to the Jupyter notebook, and then how to run R on Jupyter notebook. You appreciate the Jupyter notebook. It's technically much more better than using the R Studio. But anyway, so the C's YouTube video would also encapsulate that. You don't have to be perfect before tomorrow, no. So you can just come watch what we do tomorrow. Be engaged, be informed, be curious. Then from there, you can now go back and start the first YouTube video in my class, and then you can now watch at your own pace and up to the C's before we proceed another time. But please don't forget to subscribe. I know sometimes Africans, we benefit, but we don't want to in return by just subscribing. You pay nothing for subscribing to the YouTube channel. Okay, so please, I would really appreciate if you subscribe. Okay, thank you very much.
Yeah, thank you very much. Thank you very much, Sharif, for sharing that link. But then, if you also want a direct link to, you can contact me privately, then I'll forward it to you. Yeah, so that we can get everything rolling tomorrow. Yeah. But we are very, very happy that you joined us today. Yeah, and see you all tomorrow. Tomorrow will be more fireworks. It's going to be very, very practical. Tomorrow, I think we'll extend the time a bit so that everybody can partake, equally. Yeah. Thank you very much, everyone, and have a nice evening. All friends who join us from different countries, Russia, UK, Nigeria, Ghana, we thank you so much for joining us. And please extend the good message you heard today to your other colleagues so that tomorrow we can have more numbers. Thank you very much.
And don't forget to tell them that everything that I said today would also be uploaded on the YouTube channel as well. Okay.
The discussion we had here today or the presentation is recorded, and so like he said, it will also be uploaded on the YouTube channel. Then you can have access to it anytime. Thank you very much. Enjoy the rest of the evening.
Bye.
Okay. Bye-bye.